Okay, let's get started. Um, so uh, Today I want to talk a little bit about binary operators. I intentionally talk about this in class. I give away a little bit of the current PA by doing this, but as we're getting sort of our compilers off the ground, it's nice to go through some of this stuff in detail. Over the course of the quarter, I'm not going to do as much detailed coding during lecture, but during the first few weeks, it's just super helpful as we all get the first compilers written to see this stuff in detail in class. So that's why I'm doing some of this stuff in super detail in class. Some of you actually asked about that. I put this thing on quiz 2 where I said ask a question about the course, and people were like, well, are we going to be doing like all programming in OCaml to build up little bits of compilers in class, or like is that what 10 weeks are going to be like? And not really. As we get further and further, we will all be able to talk more and more abstractly about this stuff without having all the details of the code on the screen. That said, until we get to that point, it's really useful to do this ourselves. Okay, so this is actually I have a slightly I fixed something on your worksheet. So I'm just going to put up this version of this code, this thing right here, because I want to. Let me copy paste the right thing. I just realized that I made a final change in your worksheet right before I came in, and I want to have exactly the right version. I don't want to be talking about something else. Okay. Okay, cool. So what I want to do is on your worksheet, I actually gave you two different implementations of how to do binary operators. I put two different implementations on there. So on the front page of your worksheet, the one with the data definitions and the grammar on it, I added binary operators to the language. It's called just plus. I added e plus to the language. And so there's two implementations, and what I want you to work on first, I'm just going to go through this with you after you do it yourself, is what assembly code do we get out from running the compiler on those two implementations, right? So there's two implementations of plus, and on the front page of the worksheet, there's a little match case that says E plus, E1, E2. And these are intended to be two different possible implementations of E+. They have different interesting characteristics. Some things will work about them, some things won't. But what I want you to do is figure out what assembly code they'll generate. So do both of these. Start by filling in what assembly code we'll get for compiling both of these. Version of this. Oops. talk about it and see if you agree at least like what the first few instructions are. Yeah, you should turn around and talk. Yeah, yeah. Okay, let's go over the left-hand side, the simpler implementation on the left-hand side. Then I might give another minute for the right-hand side. So I saw a lot of people sort of diving into this. I'm going to start going through it. Keep an eye out for when I make mistakes. So we're going to start, right, keep an eye out for when I make mistakes. I might make one or two instructive mistakes. So one of the first things that's going to happen here is we're going to be getting the instructions for E1. So the first recursive call that happens is this one. And that's going to be a recursive call on the E number 1. So that's going to be whatever the E number case does, which is moving 1 into EAX. We've always said when we compile these constant numbers, we take the constant number, move it into EAX. That's the instruction that's generated for one of these constant number expressions. Okay. So that's, if we wanted to sort of color code where things are coming from here, this instruction is coming from, that's the E1 instructions, because E1 was the number 1, and the instructions for that are moving 1 into EAX. Okay. The next instruction is to move EAX into EBX, and that's just some other instruction that is going to take whatever is in EAX, which is 1, and move that into EBX. Oops, let's not make this green. Let's say that's let's call this the yellow one. Yes? No. No. I saw actually a few people, this is an easy, I saw a few people make this kind of mistake when I was walking around. This instruction is not doing any, there's no like fancy substitution that happens in the instructions that are generated. The instructions are just these strings that we're generating. So the first instruction moves 1 into EAX, the next moves EAX into EBX. These are just strings that are being spat out by this compiler. So then the next thing is whatever we get for compiling 2. And the last line is this addition. Okay. So we calculated the left-hand side. It ended up in EAX. We stored that in EBX because there's two things. So we want to be able to add them together when we're done. So we need 2 places to store things. We can't store everything in just one register if we're going to do this. And then we add them together. We add them together at the end, right? So what'll be in EAX at the end of this? 3, yeah. So this seems to have worked. Cool. So maybe we have a potential implementation here on the left-hand side that works. Okay. Take just one more minute and do a little more on the right-hand side, and then we'll go through it together. Okay, all right, all right. So what's the first instruction that's going to come out from this right-hand side compilation? The first instruction? Same thing. The same thing as in the first case, right? Here again, we have the instructions from evaluating the right-hand expression. Oops. From evaluating the right-hand expression, and that's just getting things started. So then after that, we have this sprintf of moving EAX into whatever %s is, which is stack val. And stack val is this thing that just builds that ESP location. I just put it in a helper function so that we didn't have bracket ESP floating around. If you look at your sheet, there's a helper function called stack val that generates something that looks like ESP minus something, which is the number times 4 filled in. So this is going to move into ESP minus, and I set up here assume SI starts at 0, so I'm going to write minus 0 here. We could talk about whether we need to start at 1 or 0 depending on how the stack is initially set up, but just for simplicity here I said start at 0. So move ESP minus 0, EAX. And that's coming from, again, this line. Okay. Then the E2 instructions are the same. That's just getting the value 2 into EAX. Then the next thing that's happening is we are moving into not just the stack index, but stack index plus 1, whatever's in EAX. Move ESP minus 4. EAX. And then we're moving into EAX ESP minus 0, still using stack index. And then we're adding EAX with ESP minus 4. And this part corresponds to these instructions. And that's just filling in this SI and SI minus 1 thing. What ends up in EAX at the end of this? Oh, is it a problem? Problem? So I want to set aside that that is an off by 1. If that is a problem, it's an off by 1 in how we just initialize this. And so yes, when we configure this to start running, we'll have to make sure that we start the stack index at the right place. But it's not that critical for understanding how this is working. So I agree that we might have to talk about that. The reason I picked 0 is because I have a slide that I want to show where I started at 0. So I want the example we do on the screen to match what's on my slide. That's really the reason I did it. And as for initialization, we just have to put it at the right sort of offset for however the stack looks when we start running our code. Okay, so in EAX at the end of this, through a lot of work here, we're going to move 1 and 2 into EAX, then into memory, then we're going to move them back out of memory and then add them together. Right? That seems yes, this does work in the sense that it puts the answer 3 into EAX at the end, but it seems like it took us a long time to get there, right? So why the heck is that worth it? So I want to do the second set of examples now to talk about why this might be a relevant thing to have done, all this saving. Question?
Why is it in the second example, the E2IS, instead of SI,
Ah, that's really interesting. Let's think about what would happen if that were SI plus 1. You're like going back in time. I prepared a version of this lecture where I had exactly that version as a third column. Then it was like so much writing, so I stopped. So now let's ask this question. So if this said SI plus 0, let's say, right? Like just SI instead of SI plus 1, what consequences would that have for the generated code? Have any consequences for this generated code? You first. Something about overwriting. Something about overwriting. Yeah. So something about overwriting. There's some articulation around what that means there. Say what you were going to say. We might overwrite something. So both of you are saying something about overwriting. There's some concern that we're going to overwrite something. So in fact, although we aren't going to be able to see that from this example, because actually in this example it wouldn't change anything about what comes out, right? Because we're not in that recursive call e to is, we're not using the stack index at all, because the only thing that came from that recursive call to e to ix is moving 2. Right? This instruction here is the only thing that came from that recursive call in this case. And so we can't really see the effects of changing it in this example. So let's go to the next example where we'll see the effects of changing it, right? So really good question. Okay. So next example. So like you did for the first one, I want you to work on this for a minute. Let's do the left-hand one first and then do the right-hand one. So the next example is this +5 +1 3. So there's a nested addition on the right-hand side. Let's see if I can get a nice, clean version of this copied. Okay, let's do the left-hand side. Let's do the left-hand side. I'm going to get us started. So with the same idea as the last example, on the left-hand side, we're going to first move into EAX the value 5. That corresponds to just doing the left-hand side, doing the left-hand operand of this thing. And then we're going to have this move into EBX of whatever we just put into EAX. And then we have to do whatever we get for E2 instructions. Right? The next thing is whatever we get for E2 instructions, which is going to be this recursive call with another plus expression. Right? So when we go to process this part, right, which is this E2 instructions, this is actually going to be several instructions corresponding to this recursive call to handle the +1, 3. What's the first instruction in that chunk of instructions going to be when we recursively do this for +1, 3? Move EAX, move EAX 1, okay? What's going to be, and so then we're just sort of in a chunk of these kinds of, processing these kinds of instructions. So we're gonna, that was the E1 instructions for this nested thing. So we'll have a move EBX EAX. What'll be right after that? Yep. And then we're going to finish it off with an add. So we'll add EAX EBX. And that processed the right-hand sub-expression, so the +1, 3 that was the sub-expression, right? So this part here corresponds to that region. Okay. So that's kind of cool. Seems promising. We have the right answer for that nested addition in EAX now, and our goal is when we do these, write this compiler, is to always produce instructions that'll get the answer into EAX. We have 4 in EAX. Okay. So then we'll come down here, and we'll finish this off with what's the last instruction here? Add EAX EBX, right? So this all works and puts 9 into the EAX, correct? What's the problem? What's the problem? Yeah. It results in 5. It results in 5. Whoa. Oh my gosh. Is it 5? Is 5 the right wrong answer? Yeah. So what's happened here? We said, we'll have EAX and EBX, and those will be the places we store the left and right hand operands. That's because we need to add them together later, so we need to store them in the left and right, and EAX sort of represents the right hand operand, and EBX represents the left hand operand. And yet, when we did this nested processing, we overwrote that value we were storing in EBX, right? EBX ended up with 2 jobs in this program. It ended up trying to store the left-hand operand, which was 5, and then it ended up trying to store the left-hand operand, which was 1. Now we could say, well, when we do nested operands, we need to use ECX and EDX, but we will quickly run out of registers if we try to take that approach. Right? We will very quickly run out of our finite amount of registers if we just say, well, every intermediate result from nested computation can be stored in one of them. We'll just run out of registers. So the way we need to handle this is actually to find some intermediate storage that we have a little bit more space for than just the 8 or 16 or 32 or however many registers our instruction set happens to support. Okay? So that's why we do what's on the right-hand side here. Okay? And I want to animate what's going on the right-hand side. So I'm going to, rather than just writing this out, I want to do a little example of this. So this was, I wrote this in infix notation, but this is the same expression. So I want to show where the different pieces of compiling this will go. Okay. So, whoops. So the first thing we have is getting 5 into EAX. Okay. So we can think about running this through. So that puts 5 into the EAX register. Then we take whatever value we got from the left-hand side, and this is sort of the job of plus. To store whatever it got for the left-hand side, and it's going to store that on the stack. That's actually going to be something that gets stored on the stack. Okay. Then we're going to start processing this nested expression. Now, someone asked about why do we do SI plus 1, right? And every time I indent here, I'm representing that I've incremented SI by 1. So we're going to start storing these nested values at increasing stack indexes because we're going to increment as we go recursive. That makes it so we don't accidentally keep overwriting like this bottom stack location, right? So as we go into these nested recursive calls, we want to make sure we keep increasing it. Okay? So EAX now contains 1, and this is sort of the important thing to keep in mind when you're thinking about going from these nested expressions down to assembly, is that the nested expressions have this wonderful notion of structure, like we'll evaluate the left-hand side and the right-hand side separately. The machine doesn't have any notion of that, right? There's just registers that get overwritten. There's a very small number of them. So EAX, which sort of was holding 5 before, no longer. Now it's holding 1. EAX is actually going to get overwritten a ton of times while evaluating this, right? So we evaluate the 1. We store that in EAX. Now we're going to store the value for the left-hand side into ESP-4 because we added 1 to the stack index. So that's going to be a storing of the left-hand side using this incremented stack index. So that stores 1 on the stack. Then we're going to move 3 into EAX because that's the right-hand side. We're going to take 3, and then plus is going to say, well, before I do anything, and this is maybe you're going to say at this line, like, hey, Joe, this is a little too much storage, right? Like, do we really need to store the left-hand side, which is 1, and the right-hand side, which is 3, and then add them together? Do we really need to do that? Do we really need to do that? Anyone think of why we might, like, this is a decent general thing to do? Decent general thing to do? Yeah. So if we do something like subtraction or division that doesn't have this property of being able to be reordered like plus does, then we also care about evaluating left to right, we really do need to evaluate the left, save it somewhere, evaluate the right, save it somewhere, and then start with the left and then do the operation on the right. So if we care about certain things related to order of operations, it's useful to do this. We don't actually have to use this storage in every case. For plus, it's true. We could do these, we could sort of store them in either order and then add them in either order and we'd be fine. So I just wanted to highlight that because this is sort of storing 3 here for plus is kind of unnecessary. We could just add it to 1 here and then move that back into EAX. We could shave off 1 instruction and 1 storage spot. But in general, this is a nice way to do this that avoids any problems with like left to right valuation. So then we're going to take our left-hand side, which is 1, move it into EAX. This is still processing that nested plus that I'm drawing in purple. So 1 is now the value in EAX. Then we're going to add to that, finally, its right-hand side, which is 3. And this is how we're going to get this intermediate 4 value that's the result of the nested plus. So next, we're done processing that nested addition. So we're going to go back out, and now we're going to store that right-hand side result, right? That right-hand side result we just computed, which is an EAX. We're going to store that on the stack as well. Okay. I'm overwriting part of the stack here. Why is that okay? Why is that okay? Is that okay? Is that okay? Okay. Yeah. Yeah. So it's good to go back to you since you brought up the initial sort of increment, decrement, SI issue, right? We're done processing all of the expression that used 1 and 3 for temporary storage, right? That nested expression, we're done. We have the answer. The answer is 4. We can start reusing that space now. And this is just sort of how a stack, this is like how a stack works. It's working within nested expressions instead of working between function calls, but it's the same stack logic. Right, we've used up that part of the stack for temporary storage for the nested expression. Now we're done with it. Right? So we can move on. Okay. So finally, then we can get the original value we stored, the 5, back into EAX, and then add these together and get 9. So this motivates why we have this stack index increasing and why we have this temporary storage for all these nested expressions. Right? So the actual individual primitive moves are here, and then each indent that we had was sort of a recursive call with SI plus 1. Okay. This strategy that I've presented here, this works nicely in general for anything that has sort of these nested operations where you need to store intermediate results. Right? This idea of having a stack-based discipline for finding temporary space. And then you can reclaim some of that space very easily just by starting to overwrite it. Any questions about this picture while I have it up? Yeah.
The expressions become more and more nested.
Mm-hmm.
Can you actually reuse that same stack space?
Yeah. So. Yeah, exactly. So let's imagine that we replace the 5 here with some very deeply nested expression, like 10 nested expressions deep. The thing to think about is that where I have move EAX5 there would be some long sequence of instructions that get the answer for that sub-expression into EAX, right? Be a long, long orange sequence of instructions that would do that work. That might indent a lot, right, in terms of incrementing stack index. But by the time it's done, it's going to dedent all the way back out, right? It's just going to process this whole nesting, and then it's going to all come back. Because the recursive structure doesn't, it's not like the stack index is a variable that we mutate and change, right? It just updates on these recursive calls. So for processing the right-hand side evaluation, we're still going to be using that stack index of 0 initially that we had for the whole expression. Because we'll do all these recursive calls on that left-hand side expression, return from them all, and the stack index at this current level is still 0 or 1 or whatever it was before. And so we might use like tens of words on the stack for that left-hand side computation, and then we'll just start reusing them for the right-hand side. Yeah?
Where is SI incremented? Because it's each level of the recursive call to E2 IS, right?
Yeah. Yeah. So the only place here where SI is sort of if you incremented is in these recursive calls on the right-hand side. Yep.
That's not here anywhere?
Should be.
Where is it?
It's here and
Oh,
here.
that makes sense. Perfect.
Yep.
Okay.
Yeah. Let me pull that up on the screen just because it's worth circling it since. Yeah. So the place I'm talking about is here, where when we go nested on the right-hand side, we start incrementing that stack index. Yep. And we don't increment it when we go to the when we go down the left-hand side because we're not using any temporary storage when we're evaluating the left-hand side. The left-hand side just is going to do what it does, and then once it's done, the value is going to be in EAX, and then we need the temporary storage. But when we go to the right-hand side, that SI plus 1 is really saying, don't use the bottommost word on the stack, please. I need that. I put the left-hand side operand there, so don't overwrite that. That's really what that's saying. Right? This sort of, I mean, parts of programs don't really talk to each other, but this sort of tells the right-hand side instructions to not use or overwrite what's at the current SI. So that's where we get into trouble. One way to think about this also is that when we do one of these binary operator expressions, we're sort of using the same idea as let, right? Let really used this idea of store something at the current stack index and increment the stack index so that we set aside that space. So this really is almost like we're saying turning these programs into something that looks more like let temp 5. So I'm just sort of taking this program over here and saying what it kind of ends up looking like. Let temp 5, let temp 2 be plus 1, 3, and then plus temp 2. It's actually kind of like we did something where we introduced temporary variables for these things. It's actually very, very close to what we did. We just never made up variable names for them. We just said, we're going to use these 2 places on the stack to store them, and then later we'll come back and look those values up and add them together. Okay? Yeah?
So I was wondering, does the order for the way we evaluate E1 or E2 matter? So in this case, we evaluate E1 first.
Yeah, so the question is, does it matter if we evaluate E1 or E2 first? And this is a question of the language's definition, right? It's sort of like a different question than the implementation if that's supposed to happen one way or another, right? So for example, a good place to bring this up is when you talk about actually having a function with multiple arguments, what order should those expressions evaluate in? And C actually doesn't specify it. It says any order is fine. Figure it out, compiler. You can choose any order that happens to work for you this Tuesday, right? Whereas other languages like Python and JavaScript and Java specify that they evaluate from left to right, right? And so it's a language specification question. For the current programming assignment, since it's really hard, there's actually no way to to observe which one went first because it's just arithmetic. It won't matter. In the future, when we can do things like print, it really will matter. Because if the left-hand side prints and the right-hand side prints, you'll be able to tell the difference for which one you evaluated, right? That's where it'll start to matter. Okay? So once we add like print or anything that changes state to the language, we'll be able to see those things. Okay? So I'm not going to write this one in because this one's on the slide, and I'll put the slide online. Cool. Any other questions about binary operators? Questions about that? So this idea will come up again and again, that when we have nested expressions where we need to track a value, we'll make up some temporary storage for it. Because registers will never be enough for arbitrary nested expressions. We'll talk much later in the course about ways to make this. I mean, clearly we can do better than 7 instructions for this simple example. Right? Clearly we can do better than that. And even in this example, it's not clear that we can't do smart things for plus, and for 1 and 3, it's not clear those need to be stored on the stack and things like that. So we can do better than this, and we'll talk about selecting instructions more intelligently. But what I've shown you in class today is sort of the general case that will work for anything that has these nested expressions. Okay. So one other thing I want to talk about today, just to sort of lead into the next topic. Whoops. I just want to ask you a series of design questions. And I'm not going to say much about them. I just want to ask what this program should produce, and I'm going to ask this a couple times just to see what you think. Because the rest of this week is going to be about introducing if and introducing Booleans into our language, and we have some design decisions to make in doing that. So I want to get some of your thoughts on how you think these features should work. Five, 4, 3, 2, 1. Okay. Okay, next one. Just change that to 0. Five, 4, 3, 2, 1. 5, 4, 3, 2, 1. Last one. Okay, 5, 4, 3, 2, 1. Okay, cool. Let's see if we can get these all up. So that was this one. Can I click this again? Oop. So I'll just look at them one at a time. I don't think, there we go. Compare. All right, we can only do 2 at a time. That's what compare means, I guess. All right. So question 1 was this one up there. Question 2 is this one. So interesting. Okay. So 51 people think that this should produce A, which was A was 5. So 51 people think this should produce 5. 12 think it should produce 4. And I think these were C, D, and E were C and D were error or something else. So the two something else's, I'm not sure. The E, I'm not sure what to make that one. Okay. But so 8 people said error for this one. Most people said it should produce 5. And then this one, almost everybody said it should produce 4. More people said it should produce 4 than people said that top one should produce 5. Right? Kind of interesting. I wonder if I'd put 1 instead of 2, if those numbers would have been the same. Either that or at this point people thought I was asking a trick question, so they started trying to guess. This is a design question, so I don't have a particular right answer here, just sort of criteria we could use to decide. Although I think that producing 5 in the x equals 0 case goes against what most languages would have 0 mean. 0 tends to mean a false-like thing. You know, it's not unreasonable to say 0 means true and non-0 means false or something like that. Okay. Interesting. So most folks see. Does anyone want to volunteer? There's something else. The 2 people who said something else. Yeah.
I see something else is when you need to want to like type language that's like consistent.
Uh-huh.
You should only have Boolean expressions inside each statement.
So it should be an error, right? So then it would be an error.
Or like at least 1.
Yeah. So maybe C, right? So C or D. Okay. Cool. All right. Cool. Let's look at 3 and 4. Okay. 3 and 4, so 2 plus false and 1 plus true. I guess I'll just do these one at a time so we can see the answers, because even if I remember the answers, it's hard for everyone in the room to remember the answers. So this was question 3. Okay, so this was question 3. So 47, so that's less, right? Something like 60 of you were saying the 4 and 5 answers before. So this is less consistency than before. So 47 of you said E, error. 18 of you said, well, true is like 1, so this should produce the value 2, right? That's my interpretation of all the people who chose A. A bunch of you said, well, this is like Boolean algebra, right? Plus is like or, so maybe 1 plus true also produces true, right? It's sort of like the plus operators like or on Booleans, okay? All of those are reasonably consistent interpretations. Let's see, okay, so next one. So this is the 2 plus false one. So this is very similar, a little bit of migration towards the numeric interpretation here. So for A, 21 people said this was reduced 2, which would be consistent with false being 0. And then C and D, some people said true, some people said false. That's kind of interesting. Because it might depend on if you think that plus means like an or-like thing, and then any positive value is true, or what that interpretation is. Cool, okay. That's pretty interesting. So I ask this question when I teach this course because I like to see what folks think. It's kind of interesting that when you ask the left-hand questions, more people are always okay with treating a number as a Boolean than they are with doing arithmetic with numbers and Booleans. This is the same thing I always see when I ask this question. It's not a huge number, but it was different. It was different by like 10 of you, right? There were around 10 of you who thought that there was a difference here. I think that's pretty interesting. So the reason I bring these up is because I want to point out that, at least in this case, a lot of you thought this should be an error, right? The majority of you thought this should be an error, right? In this case, the majority of you didn't, and that sort of matches existing languages. But the fact that you think these should be errors means that there are definitely these cases where viscerally in the design of a language, you want to distinguish numbers and Booleans, right? 48 of you want that out of like the 80 of you who are in the room, right? So we should respect the 48 of you, right? And make sure that we can express detecting the difference between a number and a Boolean. That's going to be an important language design point for us, is to not just say, true is 1 and false is 0. Because if we just said true is 1 and false is 0, we would capture the C-based view of the world, and maybe sort of the Python-based view of the world, depending on how you think about Python, and miss out on this entire other area of our intuition about how this stuff should work. So that's why what we're going to do next. How much time? Oh, we have a few minutes. Okay. So that's why what we're going to do next, later in this week, is talk about how to distinguish these things and detect them at runtime to raise errors. Okay. Before we get there, I want to just bring one more thing up on the screen, which is this notion of ifs. So this is the if program from the last slide. This notion of ifs, and this is in a reading in a fairly substantial way, so I'm not going to talk about this a lot in class. I just want to bring it up. And also from cse130, you sort of saw a lot of compilation of if. Let's say we want the interpretation that positive numbers are true values and like zero is the false value. And let's think about what instructions we'd get for compiling this kind of if expression. So we'd move 2 into EAX. We would compare that value to 0, so we'd use CMP to compare it to 0. So we're checking for zeroness. If it were 0, then we'd go, if it were equal to 0, then we'd go into the else branch because that's false. So JE means jump if equal. So in x86 we use the word jump instead of the word branch. So it's jump if equal to the else branch. So if it's false, go to the else branch. So the else branch is going to be down here, and then the then branch, which we'll take if we don't jump to the else branch, is going to move 5 into EAX. We need to be careful not to just always run the else branch, right? We don't want to just keep going on these instructions and run the else branch. So we're going to have, I'm leaving a gap there for an instruction. The else branch is going to move 4 into EAX. And we're also going to have a jump to after if. So this is one way to compile ifs. There's a couple different structures you probably saw when you took cse130. This is a totally reasonable one. The important thing is just that there's going to be a then branch and an else branch, and one of them is going to appear above the other in the code, and you need to make sure that at the end of one of them you jump past the other because you don't ever want to run both, right? And so that's the thing to remember about compiling if expressions. I'm going to assume that we're all pretty happy with compiling if expressions. We're going to move on to talking about distinguishing Booleans and numbers for the rest of the week, which will be our